Well, I'd say go ahead, Tyler. I'd like to welcome Tyler. Oh God, I'm sorry, Tyler Linder. Yeah, to giving his applicant seminar. Tyler, I just learned, lives in Illinois. I kept thinking he was living in North Dakota for some reason. I don't know why. And he's applying to join us. I'd recommend that he apply as a research scientist, as I was saying in a message, because he has almost a decade as a science PI on NASA awards, supporting follow-up work on NEOs for planetary defense. And he's also the assistant director of a collection of telescopes down in Sertololo. So too bad Faith isn't on here. She used to work down there, much further in the past. So Tyler, I'll turn on over to you, and maybe you could also, explain yourself, explain some of your history to folks.
Okay, will do. Thank you for that introduction. Thank you for allowing me to present my research, and hopefully we'll have fun over the next 45 minutes or so. Okay, and to confirm, can everybody see my presentation?
Yes.
Okay, so hi everybody. My name is Tyler Linder. I live in Illinois, and I'm going to talk to you today about my research project, the Ambiguous Taxonomic Asteroid Research. If you have never been to CTIO, that's the picture you're seeing from the top of the mountain. Blanco is actually the large dome to your right. My telescope is actually in the middle on the left, where the dome needs painted. That's the SMARTS 1 meter telescope. I'm the deputy director of SMARTS. Todd Henry and we manage 4 of the larger telescopes on Tololo. The telescope on your left is the 0.9 meter, and then actually the dome you can barely see on the right. That's actually a 1.5 running the spectrograph Chiron, which is doing a lot of test follow-up right now. So quick, who am I? I'm 36. My wife is Danielle. We have a son, Owen, and we live in Sullivan, Illinois. And if you know where Sullivan is, I'm sorry. There's about 3,000 people. And I was saying earlier, we are kind of one of the last stops on the internet line. So if you go about a mile beyond my house, there's no internet. So the little history of myself, after high school, I joined the Navy. I was on the USS John C. Stennis. I was trained as a 2-wire electrician, and I managed the alarm and warning systems. So I really fell in love with physics and kind of engineering there, because anytime you had a steam valve, a reactor plant, steam turbine, catapult, arresting gear, there was some type of alarm or warning system that had to connect, right? So you're talking about circuitry, analyzing mechanical positions. And there's a lot of overlap to that, what I do today of actually operating telescopes. So after the Navy, I did my bachelor's in physics at Eastern Illinois University. And kind of like the one-page history timeline of me, and this presentation is very much timeline oriented, but the one-page kind of overview is I've been funded through NASA Near-Earth Object Follow-Up programs since 2012. At CTIO, I started with a 16-inch, and now nightly we operate a 24, 1 meter, and 1.3. I also manage the telescopes here in Illinois at the Astronomical Research Institute, where we have a 24, 30, 32, and 50-inch. So I did that work for a few years, and I definitely realized I needed a PhD to stay in the field. So I started my graduate career in 2015 at the University of North Dakota. And in 2017, when I finished the master's, I rolled directly into their PhD program in the College of Aerospace. My dissertation defense is planned for the fall of 23. So we're not going to talk that much about near-Earth asteroid follow-up today, but just a quick overview. The image on the left is actually the old 2-mast telescope that had DECam there for about the last 15 years. So DECam finally failed in 2019, and we had automated it last year, and it's now in our near-Earth asteroid follow-up program. The image in the middle is a 24-inch on Cerro Tololo, followed by the image on the right. This is where the telescopes in Illinois are housed. It looks like they literally look like sheds in the backyard.
What's their elevation?
At Tololo or in Illinois?
Illinois.
200 meters.
Okay.
The picture is specifically taken so that you don't see the cornfield about a quarter mile away. So from 2012 to about 2021, all of the follow-up work between CTIO and Illinois were done by two people, myself and Bob Holmes. So over that time, this is kind of a quick overview diagram of overview diagram of kind of the follow-up system that I built. So over the past 10 years, I've taught myself not only how to run databases, but using Amazon Web Service database clusters, servers. I've written telescope automation. And so essentially this system allows me to sit at a laptop, type in a target. The telescope will carry out the observations and the data will be back on my computer within about 5 to 10 minutes. Our goal is have that data, and we're doing astrometry, so have that data analyzed and submitted to the Minor Planet Center within an hour of it coming off the telescope. So all of this entire system, we're not going to go through it. I built, and basically that's where a lot of the software engineering experience I've gained. So this is my 10-year timeline. There's a top line and a bottom line. The NASA-funded telescope operations are on the top versus my graduate work and research at the bottom. So although my graduate work is not funded and NASA doesn't give me any money for that, there's a lot of parallels because as any scientist, we use what we have available. So this presentation is kind of broken down into early stage, so basically pre-COVID, and then what I'm currently doing. So one thing to note here is that all of the grant applications I've submitted to fund my dissertation have been denied. On top of that, my UND Space Studies does not provide TA and GA to all students. So I'm in the very unique situation where not only am I paying out of pocket for my graduate work, I'm also funding all of my research myself. So there's a few things timeline-wise that we go through that there's probably better ways if somebody else was paying for it. So for the next 20 slides, we get to kind of sit back and enjoy the early stage of my research, which is 2016 through 2019. The quick summary here is that I kind of start off by discovering an issue in the Sloan Digital Sky Survey Moving Object Catalog 4. I defended my thesis, my master's thesis in 2017, began the PhD. We build the dissertation hypothesis, and then I begin the early stages of the Ambiguous Taxonomic Asteroid Research data collection. And followed by, right before COVID, kind of discovering a major issue with the data set. So let's start off by asking the question, why is the Moving Object Catalog 4 from Sloan important? So this table somewhat summarizes all of the previous surveys, if they took filtered data or spectra data and how many data points. And so although a lot of the previous surveys observed the same asteroid multiple times, if you assume it's a unique data set, there's only approximately 5,200 observations total. Sloan observed 105,000 unique asteroids. So Sloan is not important because of the resolution. Sloan is important because of the volume of the data set. And so although we don't get very precise information, we're clearly getting a large sample. So how does Sloan's observations compare to the main belt as we know? So the green line here is actually the current main belt asteroid population. It's a histogram of the function of size. For simplicity here, I assume a 15% albedo for all the objects. And you can see at the bottom where Sloan observed, and Sloan is in the orange line. So let's zoom in. So zooming in here, what you can see is that the mean size that Sloan observed is somewhere around 2.5 kilometers. But now you can start seeing in the lower left, the blue line, and this is where all the previous surveys studied. So let's zoom in again. So there's two pieces to take away from this. The first one is that Sloan did not observe all of the asteroids in the previous that were studied by previous surveys. There's actually not that much overlap. The reason for this is Sloan simply saturated the larger asteroids. So one of the easy things to do if you're trying to question the validity of Sloan data is compare with previous surveys. That turns out to be extremely difficult to do, mainly because all of the data sets, each data set is normalized at a different wavelength. And if you take spectra, you're trying to combine spectral data points to then compare with a photometry point. And so although I've attempted this multiple times, there's just simply too few asteroids that you can do the comparison to see if Sloan's data aligns with the previous data sets. So just to kind of reiterate, if you're not familiar with Sloan, Sloan observed ugriz. Each filter transmission here has two lines. One is assuming no atmosphere. The other one is an air mass of 1.3. But the key thing to note here, all 5 filtered observations were taken within 6 minutes. So it's a snapshot. So if we are assuming that all the main belt asteroids rotate slower than 2.2 hours, 6 minutes is 4%. Right? So 4% change. So we can really treat every Sloan observation as a pure snapshot. More importantly, is that Sloan did not specifically observe asteroids. It did a survey. So we're getting an asteroid observation randomly because it just happened to be in the field. So but the time between observations could be a day, a week, months, or even years. But essentially, they're just time snapshots, a perfect moment in time, but we have no additional information. No asteroid was observed twice in the same night, and there's no guarantee that you would have a second data point even the next night. So let's look specifically at what Sloan is giving us. So this plot here is I've removed the U data. So you'll see that the data points on the left are from the G filter. Everything is normalized on R, which is why everything in the middle is at 1. And then you have the I band and Z band being on the right. The question that I pose is what photometric classification, so taxonomic classification, would you give Wabash? And more importantly, when you plot the moving object catalog for published airs and propagate them through the reflectance, they're included in this plot. So the data here is taken over about 7-year time frame. So the question kind of becomes, is this variation real, or is there, is this variation real? So one of the big things that I ran into early is, if you simplify the central limit theorem, it basically says you need more than 30 observations to do statistics. Sloan never observed any asteroid 30 or more times. So statistics on a specific asteroid are not valid. However, you can be clever here. If you can't do statistics on an individual asteroid, you can compare an individual asteroid to the whole. So if you take 114,000 MOC4 observations, and this is of course a subset, I'm skipping how I came to that subset, and you plot the G reflectance of all of these observations, you end up seeing a bimodal distribution, which you would expect because of the C and S class. So if you have a taxonomic variation or a taxonomic if you have a G reflectance value less than 0.9, there's a very high probability you'll be an S, versus if you have a reflectance value greater than 0.9, you're probably going to be a C. The normal, looking at this distribution, the skewness and kurtosis are between -1 and 1. Therefore, we can use basic normal statistics in this approach. And we can do the same plotting for the I reflectance, as well as the Z reflectance. And so Z here still keeps the skewness and kurtosis between -1 and 1. So based off of this, can we classify Wabash? Well, what we can end up doing is that we can look at the range in the I band and the Z band. And the range is in I band here is 0.14, and the Z band range is 0.25. What you can end up seeing is that if you look at the standard deviations, the range in I and Z are more than 2 standard deviations of the entire population. So what does this actually look like? If you look at the Z, the large black bars on the right are actually the highest and lowest measurement. So the question is, and really where the word ambiguous comes from, is this, what is the classification using visible wavelengths? So if you go back through the literature, the first time ambiguous taxonomic asteroid, or sorry, ambiguous asteroid is introduced is in Cavarno 2010. He tries to do a photometric based classification system, and there is a subset of asteroids he's unable to classify, and he calls them ambiguous. However, he doesn't actually define ambiguous. So in the early stages of my research, we do. And we define it as if the reflectance between 2 observations in the same filter varies by more than 1 standard deviation. And the assumption here is that the standard deviation is calculated from the entire population. So specifically in the Sloan data, because we're normalizing on R, an asteroid can be ambiguous in G, I, or Z. So using this definition, we can now start analyzing the entire population in the moving object catalog. And we end up with about 63,000 asteroids observed more than once. However, by the time, if an asteroid observed more than once, you end up with a 55% chance of getting an ambiguous classification. Well, what you see here, if you start looking really carefully, if you look at the bottom line of the table, that says if N is greater than 5, so if Sloan did 6 or more observations, you end up with a 97% chance of an ambiguous classification. So there's only 85 asteroids out of 2,400 that Sloan did not get the same colors on every time it observed. So this is kind of the question that really starts my research. And the assumption is that since Sloan observed a smaller population size, is Sloan actually telling us that the smaller asteroid population has heterogeneous surfaces? Or is there an unknown taxonomic variation that we haven't taken into account for? So the next thing to do is just plot where are these 23,000 ambiguous asteroids? And turns out they span every family, every inclination range. They're essentially everywhere. And this is pretty difficult to understand. Like if there was one family that this was happening with, I think it would be a much easier story to understand, or at least explain. But this plot here is one that really kind of led to the following hypothesis. And that is if Sloan didn't get the same colors every time it observed, and the spread of these asteroids is the entire main belt, you have to kind of question Sloan data. So the hypothesis of my research is that the Sloan Digital Sky Survey observations are valid, and that there's an unexplained taxonomic variation on the smaller main belt population. The null hypothesis is a little bit more aggressive here, that basically says there's no taxonomic variation, and therefore the moving object catalog data set is not an accurate model. And the about 150 papers that have been published and conclusions made from the SDSS moving object catalog should be questioned. So fundamentally, what I'm asking is the Sloan data accurate model of the asteroids they observed? So welcome to the beginning in 2018 of the Ambiguous Taxonomic Asteroid Research. In 2017, we automated the 1 meter telescope at CTIO. So this was a perfect opportunity for me to start a bright time GRIZ observations of main belts. As near-Earth asteroid follow-up work diminishes as the full moon increases, I was able to basically take a couple nights each full moon and just sit on a few asteroids looking for rotational variations. Right away with the data set, we discovered a very weird Z-band variation in the photometry that took quite a while to kind of figure out where it was coming from. So after talking to a few camera manufacturers, we kind of finally got an answer, and it's called Etalon fringing. So this is basically one of the initial images that I sent some of the camera manufacturers trying to figure out what's going on. These are two images, G band on the left, Z band on the right. They were taken about 2 minutes apart from each other. And one of the things we noticed is that every source that source extractor identifies is actually circled in red. So what we found is that source extractor was identifying the Etalon fringes as sources. More importantly, the fringes were only occurring in data that was taken beyond 700 nanometers. So there's a little bit of variation in I, but Z band, you see this extreme variation. Now, what do I mean by extreme? So this is a little GIF playing of Apophis. And what you can see here is that the top black line is pointing to an instrumental magnitude of about 18.2, but it's in the valley of one of these fringes. And as the object moves to the mountain or the hill of it, the instrumental magnitude increases by 2 magnitudes. So not only did I question that source extractor was giving me the right answers, I ended up writing my own little simple photon counting software. And these are real counts that the image is giving. Well, it turns out what's happening is that the infrared light is passing through the chip, reflecting off the back of the camera and coming back through the chip, right? So it's basically being reflected and passing through the chip multiple times. The probability that it's going to be picked up is actually directly due to how the CCD was manufactured. Because this is a back illuminated thin, back illuminated, so it's a thinned CCD chip, these actual waves, these fringes that you see are actually manufacturing marks that were occurred in the process. The problem is we couldn't figure out a way to get the fringing to be removed from the data set. And so at the time I was using Twilight flats, and you can see one of those flats on the left. The fringing effect just simply doesn't show up in the Z band. However, I did an experiment where I took the telescope out of focus, turned tracking off, and I went about 20 degrees away from the full moon. And I was finally able to pick up the fringing. My belief here, although not proven right now, is that the reason why the fringing doesn't show up in the twilight flats is the sky is dominated by non-IR light at that time. Only when you go in dark skies near a full moon, right, so in the middle of the night, are you able to get the fringing to come out. So the pre-COVID conclusion for the 1 meter telescope here was that the Etalon fringing flats must be taken at the same exposure length as the science images. Because essentially the CCD in the Z band becomes non-linear, due to the Etalon fringes, we ran into a whole system that it's very difficult to scale. So to get Etalon flats taken at the same length as your science images, so for instance, like a 60-second flat, it's actually a lot more difficult to do. So to achieve this, what you need to do is use a variable controlled light source with a whiteboard that you can take these flats during the day. And so right before COVID, we were kind of starting to ramp up, and the plan was to install white light bulbs on the side of the telescope that could be controlled via a Raspberry Pi. The Raspberry Pi in itself would control the on-off of the light bulbs, as well as a rheostat for the light intensity. So this would allow us to have a simple script run, and if I thought I was going to need 60-second Etalon flats, it would adjust the intensity such that the image doesn't saturate and you could get a successful 60-second flat. And more importantly, because—
Can I ask you a question?
Absolutely.
These Etalon fringes, are they static? I mean, is it the same pattern, or do they change depending on where the light's coming from or how it's bouncing into it or whatever?
So that they are static. The intensity of them is dependent by the exposure time.
Okay.
And so it's basically like a second order nonlinear linearity. Whereas in the like, for instance, in the G and the R filter, the camera has perfect linearity and we don't have any issues with it. There's a slight dependence on temperature, but we have always kept the temperature on the camera at -30 Celsius, and so we never really had to deal with it. Because this telescope is operated remotely, the Raspberry Pi would allow kind of complete remote functions, would allow this entire system to work remotely. So here's the pending Etalon research. So once COVID hit, nobody was allowed onto the mountain. In 2022, NORA Labs finally allowed astronomers to start returning to the mountain, and we're currently pending right now. So in 2023, I'm hoping to finally get the remote-controlled flatboard illumination system installed. And then once that's installed, it should be fairly straightforward to then get the comparison paper between Twilight and dome flats with respect to Etalon fringes published. Okay, so now we're kind of switching to the one slide of COVID. My dissertation and research came to a halt. My son was 4 and I became the primary parent in March of 2020 because my wife works in healthcare. And then CTIO restored operations so we could begin our near-Earth follow-up observations in October of 2020. The end result is that I would work all night and be dad all day. And so my research basically was stagnant until August of 21 when Owen started kindergarten. So in the fall of 21, remember, we still didn't know as a society if COVID was going to go away, what the long-term impacts were going to be, or even if traveling was going to be allowed. So I really pivoted pretty hard on the dissertation approach and basically said, instead of using a smaller telescope to observe one asteroid at a time, we need to use a large telescope to try to repeat Sloan's observing cadence on a much larger population. I also decided that I was going to reprocess all of the SDSS photometry data using an independently developed photometry program. The argument here is that if we could use an independently developed photometry program and get the same results as SDSS, this would provide evidence that Sloan is correct without needing to take a new observation. More importantly, it would allow us to do kind of a statistical comparison if we did find a difference to try to identify where the variability was coming from. So to do this kind of large-scale processing, it required me to develop what I refer to as my data analysis pipeline. But the goal is to how do we rapidly analyze extremely large data sets? And so the quick kind of 5 steps that it takes, you need to prep the data, confirm your FITS headers are correct, calibrate astrometry using WCS, detect image sources, We're calibrating to Pan-STARRS DR2. And then more importantly, once you have the FITS images calibrated, you need to know where the asteroids are. Well, with about 1.3 million asteroids or main belt asteroids known, you actually have to calculate astrometry for each asteroid every night to then be able to determine if that asteroid is in your data. So this is a very high-level picture of how to process large volumes of data. The concept is either vertically scaling or horizontal. Vertical is you get a newer computer, you put a new CPU, you speed up your single core processing. Horizontal scaling is essentially you don't necessarily use newer equipment, but you defeat the problem by adding more and more and more computers to the problem. So horizontal versus vertical. So turns out Docker and a system called Kubernetes, which manages Docker containers, is the answer that I chose. Fundamentally here, what it takes is Kubernetes requires a master server to kind of do all the communication. And then you need worker servers, or what's also referred to as worker nodes. So each node, so each worker server, can run multiple pods, and each pod is basically like think of like a core on your computer. So you're scaling horizontally by having more pods running. So this is what I've developed. This is my current server situation, which is about 10 feet away from me. So I have 2 worker node servers. Each CPU core is running a Kubernetes pod. My worker nodes are called Dottie and Dottie 2. Each server has 2 CPUs, each CPU with 10 cores. So total between the 2 servers, there's 40 CPU cores. I've got a 10 gigabit network between them. And then the image on the bottom, or on the very bottom, I have a Dell T340, and T340 sounds like a Terminator. So I've nicknamed my master node computer Terminator. So my horizontally scaling solution is basically to use old equipment. There's a pretty big thriving used server market. So think of like companies like Dell, Amazon Web Service, like they may use a server for 3 to 5 years and then automatically replace it. Well, they offload these servers to third parties, and then you can buy essentially top of the line equipment 6 years old for a few $1,000s. So the Dottie and Dottie 2 were both manufactured in 2015, and then Terminator was manufactured in 2017, 2018. So you're not using new equipment at all, but it's cost-effective equipment. So one of the questions that I've been asked is, okay, well, if I'm a graduate student at UND, why couldn't I use their computing center? Well, they have on-demand time, but it requires you to pay for that time, and my dissertation is not funded. The second thing is they have open time, free to all students, but they limit you to 200 gigabytes. As well as Kubernetes is not allowed because their computing solution is vertical scaling. They're trying to get you better equipment to run a single code. The data set that I'm working with between SDSS and DECam is 35 terabytes. So I can't even upload data quick enough to keep the 200 gigabytes fed. So it's just simply a different problem that I've had to solve using my own resources versus trying to have somebody else compute. Okay, so what's the status of this processing? So I have it's about 4.7 million images. And the time span of the SDSS data photometry spans about 14 years. Currently, the Kubernetes system is building the nightly astrometry for each numbered asteroid over the entire time frame. I'm actually going to limit the analysis to numbered asteroids as of today, because when you run a numbered asteroid backwards, you will get excellent RA and DEC uncertainties. So the problem that you run into is that if you take an asteroid that's discovered today, look for where it was a year ago, your uncertainty growth actually grows quite large in the past. So because I'm starting with some of this data analysis, Sloan's data goes back to 1998. If I use numbered asteroids today, I get excellent residuals going back that approximately like 24 years. The total processing time with the current hardware is about 4 months. I do plan on publishing the data in a few stages, but more importantly, I can reduce the processing time by purchasing more used servers. For the dissertation specifically, only a small subset of the SDSS data needs to be processed to allow direct comparisons. Okay, so collecting new observations. So the other part of the fall 2021 replan of the dissertation is we wanted new observations. So I was awarded telescope time in 2022A. Due to weather, the observations actually got delayed till August of 2022. And the observing cadence was to collect 7 sets of VGRIZ observations, each set spaced 30 minutes apart. So in total, it was about 610 DECam images, which turns out to be a little under 38,000 individual FITS images, and we observed 2,000 asteroids, and this was during full moon. And when we publish, we believe it should be the second largest visible data set of asteroid colors behind Sloan. So this is kind of the heart of what I'm working on right now. What I expect the DECam observations to tell us were, the observations were taken along the ecliptic. So the sample size actually has inner, middle, and outer main belt objects. It's dominated by low inclination objects with a mix of higher inclinations that, they just happen to be passing through the ecliptic. Because we repeated it 7 times with a 30-minute delay, if there's taxonomic variation, we should see the change over 3.5 hours. This isn't an absolute statement, but if the taxonomic variation is rotational based, we have a pretty good shot of seeing at least something change over 3.5 hours. We did the V observation to give us a really high signal to noise light curve. But more importantly, because we expect each filter to vary during the rotation, what we can end up doing is do like V minus R, V minus G, V minus I. And that subtraction value, you can look for changes. So how did that filter change compared to the V filter? This is going to allow us to actually measure much smaller variation changes and then look for trends in a much more automated way. So we observed it was about 2,000 asteroids. So the entire data set of observations is roughly 14,000. So we will be able to get the mean and standard deviation from the population that we collected. One of the pending questions that's not known yet is we don't know, or I should say I don't know yet, if how successful direct asteroid comparisons to SDSS will be. I believe it will be possible because I'm calibrating all of the DECam data to pan-stars. I believe if I go back to the SDS data, also compare that or calibrate that to pan-stars, I believe it will allow us to do a direct comparison then, but I just don't know how fruitful it's going to be yet. So to go back to our kind of early slide here of all the previous surveys, and SDSS is still at the bottom, this is what we're expecting this publication to be. So number of data points will be 4, but we're looking at about 2,000 asteroids to be published. Okay, so the status of the DECam data. So the data analysis pipeline and Kubernetes are built and running. About 4 or 5 months ago, I discovered this weird photometry error with Source Extractor. What was actually happening is Source Extractor was detecting faint galaxies as point sources in the data. Well, turns out when you're calibrating to pan-stars data is giving you a galaxy magnitude. So we were getting this large photometry error when calibrating to pan-stars that didn't make any sense until we found out that it was actually a galaxy appearing to be as a point source. So what I developed in late January is a completely new photometry calibration based off AstroPy and PhotoUtils, where we're PSF fitting all the images and all the sources. By doing this, extended galaxies are identified in the 2-dimensional PSF fitting, and then I can remove them from the calibration process, and our photometry calibration now looks phenomenal. So the results are currently under review. I'm not showing any of them today, but the planned paper submission is for 2023. So the next steps for my research. So server upgrades. So servers running at your office, surprise, surprise, produce noise and heat. I've currently maxed out the available power draw on my office circuit of 15 amps. So I'm trying to find a couple different vendors. There's a concept called co-locating, where you take your servers and provide that and give them to a data hosting provider and then pay them a hosting service or a monthly hosting fee. But then you still have full control of your data. But they have larger UPS backups, have higher speed internet, etc. If I do this, it'll be really easy to add a third and fourth worker node, and this would essentially double how quickly I can process by increasing horizontal scaling. I currently have 4 proposals either pending or kind of in the works. So the first one is that I'm submitting a DECam survey proposal to continue this, to collect more observations. It's due March 31st. I am looking at a solar system observation proposal in July of 2023. There's a rolling submission date. I want to submit that paper after the DECam results are published to show that I can successfully do the work. We have a NASA YORP proposal to continue our near Earth object follow-ups due in June. And then I currently have an NSF proposal pending with Texas A&M that would actually build a near IR camera for CTIO. This would allow us to do ZJHK observations of main belt asteroids. Currently, the status of publication is I've got the Etalon comparison paper that's pending once we finish that work. I'm currently working on the DECam results paper and then the SDSS reprocessing papers of 2 or 3. My last slide here is why do I want to work at PSI? Well, effectively for the last 11 years, I've worked by myself. I am very much looking for a larger community to build larger collaborations. And more importantly, I truly value seeing the success and failures of others, not people failing, but how they've attempted to solve a problem that hasn't worked. That's the one thing that I think I can clearly say over my 10 years. I haven't got to see that. And that's what I very much look from a larger collaboration, an organization to kind of be a part of and understand. Questions?
I love it. It's kind of like old school on steroids. Any questions anybody has? Something in chat.
Yeah, I typed something in the chat, Mark.
Okay.
Hi, first of all, hi neighbor, Tyler. Not quite a neighbor, but I live in Naperville, Northern Illinois.
Oh, nice.
I'd love to see your observatory sometime. I'm curious because I had not heard of the Astronomical Research Institute before, and that's really cool. But I'm wondering, looking toward the future, I am not a planetary scientist, by the way. I am an astronomer. But I was wondering, looking toward the future, whether you could see or speak to what the Vera C. Rubin Observatory, what the LSST might bring to your research.
In my current analysis, none. Okay. Because if you use the assumption that we need a snapshot, so if an asteroid is rotating, you need to be able to get all the filters collected in a very short amount of time. Well, it's my current understanding that Rubin is the system itself can only hold 2 filters at a time. And so if you can only collect 2 filters a night, the asteroid rotation will occur much faster than essentially the filter change cadence.
Right. Okay.
So I think the limitation specifically for the ambiguous taxonomic side is going to be very difficult. I think you could help solve it by, if you get so much data, so many observations on the same asteroid, you can kind of work it out, the light curve over, say, months but it's not going to be the snapshot approach to be able to directly compare to Sloan. So the
voluminous data that you're going to get by the full sky repetition isn't going to be able to make up for that, statistically speaking, you think?
That's my current belief. Now, okay. I would love to be corrected, but you could solve it statistically, but I think you're still going to have quite a few errors, and the error is going to just simply be rotational variation, as well as the distance the asteroid is going to change from night to night. So I think there's enough variables in there that's going to make it very difficult to answer the specific question I'm looking at.
Thank you. Thank
Plus
you.
phase variation, plus you're looking at different parts of the asteroid, if you're trying to integrate stuff over like a year or something.
Yeah, and you basically have to solve all of those variables. So
Yeah.
I'm not saying it's not possible. I think at least on the surface, it would take multiple years before you kind of get that data volume.
Yeah, you have to actually build up a triaxial, ellipsoidal model of each target.
Yeah,
Oh, I just noticed Susan wrote something in the chat too. Susan Benici.
Yeah, I'm looking at this for Kuiperbelt objects, but I'm not looking at a snapshot approach. I'm looking at a statistical approach over sort of years of the survey. So Grace, if you're interested, you and I can talk offline about it. Or if you join us here, then maybe that's something that we could look at for asteroids as well.
Does your system pick up any KBOs, Tyler?
I have not specifically looked. So we observed at 99% full moon.
Oh,
And so our data only goes down to about 20.6, 20.7. But in future DECam observations, if we can get dark time, then I think there's probably a legit chance that we can pick up KBOs.
Yeah, the DECam system does a great job of picking up KBOs. But not in the way that I have collaborators who are using the DECam system for other purposes and they're finding KBOs, but it's a very different setup probably than what you're using. I kind of came on late, but
so who owns the Astronomical Research Institute telescopes in Illinois?
My colleague Bob Holmes, basically his corporation or his not-for-profit owns them.
Huh.
He built them all. He built basically all of them himself.
Oh gosh. I love the enormous amount of initiative in all this work.
Thank you.
So. And so I think you mentioned that you're doing stuff with Vishnu as well, or it's part of the planetary defense stuff. What's that work?
I will let him talk about that. I don't know how much is public. But like I'm not trying to be facetious. I don't know. I don't know where the barrier is at.
Yeah. Well, I mean, excluding artificial satellites, I assume that you're doing some asteroid observations as well.
Yeah. So basically, because of the remote observing system that I built for Chile, which is being able to control telescopes remotely, I've modified my telescope system for him to then use, or my telescope control system for him to use for his research.
Mm-hmm. Mm-hmm. Any questions from other people? Well, Tyler, I'd like to thank you for a very, very interesting talk. It's amazing work that you're doing.
Well, thank you very much.
Yeah. So we'll go ahead and think we can stop recording.